This is probably my favorite problem out of the set because it reviews everything we've done. Can't put one like this on the final though. I think it's just too long. And the nature of Work It Wednesday problems are short problems that we do. So we never got to do one like this. So I want to, even though it won't be on the final, I want to walk you through it so you can see how these work. And so what happens is you raise this pendulum up to 60 degrees, you let it go, it comes down, it hits the ground, and it gets a new velocity going up, and then it bounces back up to a height when the velocity is 0. That's the maximum height, and it's asking you to find the maximum height after it bounces. And so the reason I like this is because it involves both energy and momentum. So from the ball being at 60 degrees down to when it's horizontal just before it impacts, that's a conservation of energy problem. And then from just before it hits while it's going down until just after it hits when it's going up, that's a conservation of momentum problem with some impulse and also this coefficient of restitution impact. And once you have the velocity going up, you can figure out how high it goes by using energy again. So it's energy, momentum, and then energy. So it's 3 problems in one, so let's go over this. So it starts off at 60 degrees, and so the distance from O to the center of the sphere, I think there it is 2.3 feet. And so if it's at 60 degrees, the vertical elevation is 2.3 times sine of 60 degrees. The distance from O to the center of gravity of the rod is just 1 foot. And so the height of the rod center of gravity is 1 times 60 degrees. So there's the center of gravity of the rod, and there's the center of gravity of the sphere. Okay, so afterwards, the rod is going to be horizontal. Okay, and so before you start, you can get the mass of the rod, 7 pounds over g, the mass of the sphere, 8 pounds over g, the moment of inertia of the rod, slender rod, 1/12 mass times length squared, and I can't remember offhand for a sphere. You'd have to look on the sheet, but it's mass times radius squared times some constant. I can't remember what the constant is right now. I'll let you look that up. But anyway, you can get all the masses and moments of inertia. So before, there's no velocity, so all the kinetic energy is 0. This is released from rest, typically. And then the mgh is the weight times its elevation above the datum. And so I went through the geometry to how to get those heights. Afterwards, there is no mgh because it's right on the datum, and it just has kinetic energy. So it's 1/2 the mass of the rod times the velocity of the rod, which is omega times 1. The distance from O to the center of mass is 1 for the rod. 1/2 mass of the sphere times the velocity of the sphere, which is omega times 2.3. The distance from O to the center of the sphere is 2.3. And then there's just 1/2 I rod omega squared, 1/2 I sphere omega squared. And so again, because this is a rigid body, remember every point has the same omega, so you don't have to write omega rod and omega sphere. They're all just omega. So the only unknown in this is omega, and I'll leave it to you to solve for omega. So we know the omega just before it impacts the ground. Okay, so next we're going to do momentum and impact. And so this is how you do it. You write all the MVs and I omegas before, and you write all the MVs and I omegas after, and they're going up. And in between, what's causing that change is the impulse. So you draw the free body diagram, and you integrate that thing from 0 to delta t dt. Basically everything in there is unknown. And so you can't really solve this. But if this were a momentum problem where you're given the forces, this is what you would do. Instead, what we're going to use is this coefficient of impact, 0.85. The definition of that is 0.85 is the velocity apart divided by the velocity together. What it's saying is that after it bounces, the velocity apart is 85% of the velocity before the collision. So coming together, we know the velocity of the ball is 2.3 omega, and you just solved for that omega. And so that means afterwards, the velocity coming up away from the ground is 85% of that. So 0.85 times 2.3 is 1.955 omega. And so that's a number you could get. Another way to think of this is the omega apart is that 1.955 omega divided by 2.3. Well, that just comes out to this 0.85 omega. So the omega going down is omega, and omega coming back up is 0.85 omega. But either way, you can get the number for the velocity going up or the omega going up. So once we know the omega and the velocity, we can get the new height. And so here we have the energy problem. Now all the initial potential energy is 0. It has all kinetic energy. And at the end, it'll have potential energy and no kinetic energy because when it reaches its maximum height, the velocity is 0. So we have going up 1/2 mv rod squared plus 1/2 m sphere v sphere squared, 1/2 I rod omega prime, meaning the omega after the impact squared, and 1/2 I sphere omega prime squared. Remember, all the points on a rigid body have the same omega. And using the kinematics, the velocity of the rod is 1 times omega, and the velocity of the sphere is 2.3 times omega. And remember, omega prime, you solve for. You can put all these things in here. Everything on the left-hand side is a number you can solve for. And so afterwards, the potential energy is the weight, the mass of the sphere times g, times the height of the sphere, mass of the rod times g, times the height of the rod. And we want only one unknown. And if you look at the similar triangles, you can see that the height of the rod is 1 over 2.3 times the height of the sphere, because the radius to the rod is 1 and the radius to the sphere is 2.3. And so if you plug everything in, I've done it for you here. There's V rod, there's V sphere. You can put a number in on the left-hand side here. And the only unknown on the right-hand side is now the height of the sphere. And you can solve this for the height of the sphere.